In this video, I'm going to be doing a rotational motion and torque overview for AP Physics 1, which will be a good review for any high school physics class or introductory college courses as well. First, we're going to take a look at translational versus angular variables. So at this point, you want to make sure you have a good foundation of kinematics and forces, along with momentum and energy, to make sure that you can fully understand angular motion. So everything that you've learned up to this point has mostly been translational motion, but now we are changing it and taking a look at angular variables, equations, and concepts. Secondly, we're going to be taking a look at torque, different concept scenarios and formulas that cause angular acceleration. And then third, we are going to take a look at the moment of inertia, so rotational inertia, and how it pertains to angular momentum and how mass is distributed for an object. And then finally, taking a look at rotational energy and all different concepts associated with that and with rolling objects. So let's go ahead and get started taking a look at translational versus angular variables. So let's take a look at this table with translational and angular values. So translational values are the ones that we're a little bit more accustomed to. It is when all the particles of a certain mass are all moving uniformly in the same direction. So basically something actually moving across a room, moving down a street. We have a delta S, which is basically like the delta X. A delta S would just be like moving in a specific arc. That is in meters as usual for any kind of distance or displacement. And the velocity is how many meters you're moving per second. Acceleration is the rate at which your velocity is changing, which is meters per second, shown as meters per second squared typically. Time is in seconds, showing the amount of seconds that has elapsed. Force is the amount of push or pull measured in newtons. And then we have a mass that is in kilograms as our standard unit. Now we're taking a look at angular values. Now we're concerned with variables that are very similar, but definitely a little bit different. So now when we're talking about angular motion and we're talking about rotation, we're more focused on the actual thing itself rotating. So if something is rotating, that means it has an internal axis. That basically means the thing itself is spinning. So kind of like an Earth day, as opposed to something like an Earth year where the actual thing is spinning itself and has an internal axis. So we have a delta theta, and oftentimes people are a little bit more familiar with degrees, and theta is also expressed in radians as well, which you may or may not be as familiar with. And a radian is the ratio between the S and the R, the arc length and the radius, as shown in the picture over here. So we have a delta theta, which is in radians. We have an omega now. So instead of meters per second of how many meters you're traveling across a certain space per second, it's how many radians you are rotating per second. The alpha is how many radians per second you're gaining or losing per second, which is radians per second squared. We have time, which is just time as usual. And then we have torque. And then torque is typically in a Newton meter. So a torque is basically any force that causes a rotation. So these forces mostly cause linear motion, like sliding something across a room. This torque might just be spinning a wheel or an actual person rotating. And then instead of the inertia from an object just having a certain amount of matter, it is based on its moment of inertia or rotational inertia, which is in kilograms times meters squared. Here's a few other formulas. Those are not on the AP1 formula sheet, but things that you may use. You can get theta, omega, or alpha by taking any of those linear values and dividing it by r. That might be something to just keep in mind or keep in your notes moving forward. Now, what you can do is you can use all the same formulas that you were using before, but it's just replaced with the new values for angular motion. For example, we have our theta equals theta naught, our initial displacement. plus omega naught times t plus 1/2 alpha t squared. So that is typically the most common formula you may use. The second one is going to be omega equals omega naught plus alpha t. Now, there is a third kinematics formula that is fairly popular, which is the v squared equals v naught squared plus 2a delta x1. That one is not on the AP1 formula sheet. You could also use that if necessary, which the version of that in rotational motion would look like this. Where instead of taking the linear values that typically look like this, we were replacing it with all of the rotational values. So as you're solving these angular problems, it's basically going to be the same sort of kinematics you've been solving for with translational motion. You just have to change your perspective or lens at which you are viewing these problems in terms of radians. So how much of the circle are you sweeping through? One complete circle equals 2 pi radians. So if you have something that says 5 rotations or 5 revolutions, you can go ahead and take 5 times 2 pi, and that'll give you your delta theta. And then as far as your omega goes, you're looking at it in terms of how fast it's rotating through the circle per second. This is the rate at which you are gaining that omega, and then time is the same. And then we'll get into torque and moment of inertia a little bit later into this video. Now let's move on to discussing torque. Torque is any force applied a certain distance from the axis that causes a rotation. So our first example we're going to take a look at is this wrench over here. And if you apply any type of push or pull to this handle in a certain way, it'll cause it to rotate, hence causing it to be a torque. So torque in this sense is going to be force times R, which is the lever arm, times the sine of theta. Now, when you're taking a look at it, we have a certain force being applied. We'll go ahead and call that FA for that applied force. And one rule about torque is that the force that is parallel to the lever arm doesn't cause any torque. So if you had any kind of force pulling or pushing left or right on that handle, it's not going to cause any rotation at all. Now, the portion of the force that causes the rotation is the part that is perpendicular to the handle. So if we take this angled force and this 25 degrees, that's 25 degrees from the horizontal, we can make a triangle with an x component and with a y component. And the y component is the only component that actually causes the rotation. So what you would do is you would plug in the FA, this applied force over here, whatever number that may be, times the R, which is the lever arm. The lever arm is the distance from the axis of rotation, which would be from here to about here, whatever that distance may be, and then times the sine of theta, which is basically going to give you this orange portion over here once you multiply it by the sine of that 25 degrees. The way I think about it is that sine of 25 degrees is almost going to give you like a percentage of that force that acts perpendicular to that wrench handle that causes a certain rotation. If it's pulled perpendicular to the axis straight up and down, then it's going to be sine of 90 degrees, which is 1, which gives you 100% of that force is going into rotating that object. So once you take that applied force, that lever arm, and that sine of 25 degrees, that's basically giving you the torque caused from this orange vector over here. But you don't necessarily need to find that component of the triangle on its own. The sine of 25 degrees is going to go ahead and take care of that for you. Okay, going on to our second scenario. We have two objects that are bouncing and causing a net torque of 0 Newton meters, which is a common scenario to look at. And we know that the net torque is 0 because of the plank being completely balanced. We have a certain force of gravity, which we'll maybe call, we'll call this one M2G, and then we'll call this one M1G. And those two forces are causing a torque. Now, if you take a look at the scenario, it doesn't look like you're rotating it because a wrench, you like actually physically see it turn. But since this one is static, we have two things that are causing a torque that are canceling each other out. So this force over here is attempting to rotate this plank clockwise, and this force over here is causing a torque, causing it to rotate counterclockwise, and then those two forces would be canceling each other out. So we know that 1G times that lever arm. So maybe we'll call this lever arm R1, and then maybe we'll call this lever arm R2 minus our M2G times R2 would equal 0, which basically means that these two are equivalent to each other once you add this one to the other side. Now, the only other thing to consider would be this, if the actual plank itself has a significant mass. Now, if the plank itself has a significant mass, which all you would do is this, you would take a look at the amount of the plank that is on one side, and then you would find the center of mass of that section, and then it would have its own little mg causing torque on that side, and then same thing with this side. You find the center of mass of this part, and it would have its own little mg. Okay, for example, if the entire plank was 4 kilograms, then this would be 2 times 9.8, and this would be 2 times 9.8 as well. And each of those would have their own little lever arm. As I said, that would be the midpoint of this half of the plank, and then the midpoint of this half of the plank. It isn't always centered. It could be sitting, a third of the way from the center. The plank could really be placed anywhere. So you just have to find the center of mass, or the geometric center of that portion that is on that side of the axis. Okay, now taking a look at our next one is taking a look at a pulley system over here. So these ones can get pretty complicated. The main idea is this, that we have a force of tension pulling this part down, and we have a force of tension being applied this way as well. So this would be something like a T1 and a T2. We could tell that based on the mass that's hanging on this end is that this T2 is going to be a little bit greater. So let's go ahead and make this vector look a little bit greater. And what you would do is you would still subtract the two to get the net torque, except the net torque isn't going to be 0. So what it would look like is this. We know that this is going to be a little bit larger than the torque caused by T1. So let's go ahead and say T2 times R, which is the radius of the pulley, minus T1 times that same radius of the pulley, equals our net torque. And then our net torque is going to be I alpha, which is basically Newton's second law, which is ma. And then the equivalent for angular motion is going to be the moment of inertia or rotational inertia of the disk times alpha, how many radians per second squared that the system is accelerating. All right, lastly, let's go ahead and take a look at this ladder or plank leaning against a wall. And we're going to go ahead and analyze the final torque formula, which is torque equals the perpendicular radius times the force. And basically what that looks like is something like this. Say, for example, you have a bucket hanging on a ladder or a plank over here. What happens is it has a certain force of gravity pulling it down, which is mg as usual. And then the radius perpendicular to it is going to be this one right here in orange, this distance from here to here. That is your lever arm or radius that is perpendicular from this pivot point over here. Because remember, this ladder or plank over here is attempting to pivot or rotate, but it's bumping into this wall over here, which is also causing a counter torque. But if you were taking a look at this formula right here, this is another option of something you can use. You don't necessarily have to, but something you could utilize of using a force that is applying some kind of torque. and then using that radius that is perpendicular, the axis of rotation being right over here. Now, one last idea I'm going to point out on the screen is taking a look at these different objects. And these different objects over here have their mass distributed in different ways. The farther the mass is from the axis of rotation, the more rotational inertia you have. So these are a bunch of formulas, none of which are on the AP Physics 1 formula sheet. So if you need one of those, it'll probably be provided within the question. But the main idea is knowing that the more mass that's away from the axis of rotation, the more rotational inertia or resistance it will have to rotating. For example, this hoop over here that has an axis that's right through the middle of it, all of its mass is distributed as far as it possibly can. So it has a coefficient, an invisible coefficient over here of 1, which means it has the maximum amount of rotational inertia, as opposed to something like this disc or cylinder that has half of the amount because the mass is distributed a little bit more evenly. So the rule is basically that if you have more mass towards the center, something is going to have less rotational inertia, thus in most cases is going to rotate a little bit more quickly and easily. Okay, so with that idea in mind, let's go ahead and slide over to the next topic, which is angular momentum. Now, for our final couple of topics, we're going to be taking a look at angular momentum, and we're going to be taking a look at rotational kinetic energy as well. And we are going to tie in the moment of inertia into both of those ideas. So in this picture over here, we have a figure skater that is rotating. And as they're spinning, one would analyze the formula L equals I omega, where L is going to be the angular momentum. The I is going to be the rotational inertia or moment of inertia, either one. And the omega is going to be that angular velocity. Now, when you're taking a look at these values, basically how it works is that the angular momentum is conserved as long as there is no external forces. So if the system is basically just the person over here and they're spinning on a frictionless surface over here, then we're going to say the angular momentum is conserved, which means that would be the product of your I and omega would be the same exact number. So what happens is if you increase the rotational inertia, then you would decrease the angular velocity, and vice versa. If you were able to decrease that moment of inertia, then your omega value would increase. Now, how do you do that while you're spinning? That's all based on the distribution of mass. So, as we were talking about before, those different shapes, as your mass moves farther and farther from the axis of rotation, the axis of rotation would be right over here through the person's body. If you take your arms and legs and you put them outward, then you are increasing the rotational inertia. So the way you do this is you move your mass farther from the axis. So that's the axis of rotation. Okay, and then vice versa over here. If you take your arms and then you tuck them in and you bring your leg and you bring it inward and you bring that mass towards the center, you still have the same amount of mass, but the way in which it's distributed is different. So if you bring that mass closer to this red dotted line, then your rotational inertia decreases, hence causing your angular velocity to increase. So the amount of radians that you would go around per second would increase and you would see the person spin much faster. Now, that same thing applies to people and things. One of the classic cases would be taking a look at an object that is rolling down a ramp. So we might have an object up here, and as it's rolling down the ramp, we have a couple of different things going on with it. So let's go ahead and take that object and pull it out over here. And here's the surface right underneath it. And if we were to draw the forces acting on it, we would have mg as usual, the force of gravity. We would have a normal force perpendicular to the surface, and then we'd also have the force of static friction. Okay, the reason why it's static friction is because the ball itself, if it's rolling and it's not slipping, slipping would be kinetic friction because it'd be the same area or part of that object that is going against the surface itself, but it's just each part of the ball or disc that is touching that surface and then getting pushed back as it's trying to slide, and that causes it to rotate. Now, that FFS actually causes its rotation. So there is a certain radius for this object, so we'll just call it a disk. And if you were to find the torque of that force of static friction, you would get your force of static friction by possibly doing the coefficient of static friction times the normal force, and then times r, the radius, which would be the actual radius of the disk itself. Now, as that thing is rolling, it is going to have a few different types of energy. Now, if you're using the conservation of energy, then the initial energy equals the final energy, and that's in the instance that there is no work being added or subtracted to the system. So in this case, we are not taking a look at any work being added or subtracted to the system. So we're saying all the initial energies sum up to the final energies. Now, because the object is off the ground, it definitely has some gravitational potential energy. And if it remains at rest in the very beginning, then it doesn't have anything else. But then afterwards, it's definitely moving. Now, it's moving in two different ways. It has a KT, translational kinetic energy, and has a KR, it's rotational kinetic energy, because it is actually moving across this distance, which is the KT, the translational or linear type motion that it has, and it has KR, which means the object itself is being rotated. So if you were to take a look at these different things, we have KT, which is 1/2 mv squared. We have KR, which is 1/2 I omega squared. And then we have gravitational potential energy, which is mgh. Now, if you're comparing different things that roll down the ramp, what it would look like is this. Now, one of the classic cases to be looking at would be a ring versus a disk. So our ring has all of its mass distributed as far from the axis of rotation as possible, and the disk has all that mass evenly distributed. The I formula for each one of them would be this. For the ring, it would just be mass times radius squared. For this one, it would be 1/2 times the mass times the radius squared. So the ring has a lot more rotational inertia. So if you want to see which one would win the race going down the ramp, assuming that they're the same mass and same radius, all you'd have to do is analyze it like this. If you have the UG, and then if we subtract the KR from both sides, then that would equal the KT, the translational kinetic energy. Now, the translational kinetic energy is going to be the thing that tells us which gets to the bottom first and which one is traveling more quickly at the bottom. Now, the way I'd look at it is, now that we have our gravitational potential energy, that's going to be the same for the ring and the disk because they have the same mass, they have the same value of G, 9.8, and they start from the same height. So this is going to be the same for the ring and the disk. And then for the KR, the rotational kinetic energy, the way I would look at it would be like this, is that because the ring has a lot more of its mass distributed away from the axis, the force of static friction is going to have a much harder time rotating it around. So it's going to make that rotational kinetic energy go up, and then therefore cause the kinetic energy, the translational kinetic energy, to go down once you subtract this larger number here. And then that would mean that the ring has a lower translational kinetic energy, which means it has a lower velocity. Now, to work out that entire problem is a pretty lengthy process with a lot of substitutions. If you would like to see how that's worked out, you can go ahead and click on the link above and then see how all those numbers are substituted out and then solve for it to find that exact velocity. So that pretty much sums things up. We went over all the different angular variables, taking a look at all the situations with torque, talking about rotational inertia, angular acceleration, angular momentum, and lastly, rotational kinetic energy. So I hope that was helpful to you. Thank you for watching and listening.